Okay, so okay, today we're going to talk about this WKB approximation, which is this three letters and stand for name for these three guys. Okay, right. So, well, this is another way that we could solve a quantum problem. Okay, with somehow, yeah, you don't need to solve it directly. Not really directly, but you need to solve that in the case that actually your potential is a bit weird. Okay, let's see the motivation, right? Suppose that you have like, this is potential level, right? And so this would be your energy. Suppose that this could be infinitely long for make it simplicity, make it simple, and this is going to be your energy level, right? You know that with this you could solve for your solution, right, from the Schrodinger equation, and then you find out that actually you're going to get a wave like this, right? Okay, and you could compute the lambda, right, which is what is it? This P over this is the Broglie, right? And we could explain it in terms of the wave vector here, where is the k is this one. Okay, so you see that this k proportional to somehow square root of the v. It means that if your v changed, your k would change, and then of course your lambda also change, right? That is the thing. And so suppose that now we interested in the case that your potential is like vary from this a bit. Oh, sorry. This would be variation, right? Which is very tiny. Then it's, you can with this argument, it means that we still use this lambda somehow. That is the thing, because it's not that kind of different, right? Then we somehow still can use this kind of lambda. That is the motivation, right? So now to come to the point that actually, so you can see that, so if it's if your potential change slowly, right, that is the key, right? Then so this method is good to approximate a real solution when the potential is not constant, but slowly varying, right, in space. Okay, this could be the key idea, right? That actually related to this what I did explain earlier. All right, so hope you get the point. Okay. All right, so we of course we consider the Schrodinger equation. Okay, which is taking this form. For simplicity, I'm going to consider for the 1D case for simplicity, but you can extend to the case that actually the higher dimension. Okay, so now we have this equation, right? It should also depend on x here. So this V, okay, grow fast as x. Okay. So that the classical particle is confined, right, for any E. Okay, so you need this kind of boundary. This is the boundary condition to make sure that actually your particle will be contained in the area that you consider, but actually the whole space, right, in this situation. Okay. What do you mean? Well, it's kind of, yeah. I'm not sure what do you mean, but what we consider here is that the thing, the chain, we consider only the chain of the potential with respect to space. Yeah. Yeah, only space, not the time. Yeah. But it might be. I don't know. I'm not sure. You have to have a look. Okay. So now we take a look. Suppose this should be the x, and it should be your energy level right here. And suppose that okay, suppose that this is the shape of your potential, right? So we have this point I call x minus, and this point I call x plus here. So these 2 points call turning point in classical context, right? You know that, right? Your particle, your classical particle cannot go beyond this point, right? Right. Okay. So if you solve for this turning point, what do you get? Now we define the local momentum, right? Local wave number. Okay, so this momentum can be solved from the definition of the energy, right? You're going to get this one. It's very trivial. And so the connection with this P with the wave number through this relation, right? And then what we have is that okay. So now your Schrodinger equation can be put in this form, right? Because, well, you know that this is very basic, right? And so yeah, next is a very interesting feature, all right? I would like to put star here, some here is interesting feature, right? Okay. If we take the wave function in the form okay, this one. So this A and S, they are real function, okay, of x, okay. So you plug this wave function into this new Schrodinger equation. What do you get? Let's see. So what you get is that A, this one, okay, A, right, you will get this one. And then you do this kind of derivative. So you do the first derivative, you will get A prime. What I mean by A prime is the derivative, with respect with its argument, and you get S prime. Okay. All right, here. And of course, you need to do another derivative. Then you get double prime here. Okay. And actually, it's quite a long one, because you need to take care the whole term. Okay, this is the whole bit of second derivative, and plus with this k square a equal to 0, right? And so it is not difficult to see that actually all the exponential term can be taken away right here. So it left you with and then you do you simplify it, right? You will get this kind of thing. Okay. And you could see that the first term represent this is we call a real part, right? And this would be the imaginary part. Okay. So it means that this equation will hold if and only if the real part must be 0 and the imaginary part also must be 0, then you get 0, right? Then that is a condition that we are going to look now. So first condition, your part, right? You will get square, which is actually this one. Is it? Yeah, that's right. And of course, then the second imaginary part so what you get this equation, right? And you can further simplify it to be this one. Okay? Is it? Agree? Okay. So, here come to the point again. Okay, I put this 2 stars here. Here again, it is a point so the WKB approximation will work if the term which will actually go with h bar square okay will be ignored. Okay, if x noise means that this term will go away, right? So you get very simple equation now, right here, which is this p square must be greater, right? Yeah, otherwise you cannot throw it away, right? That is a condition. That is a condition right here. So it's so for this whole business, this is also mean this also means that your s times square must be greater than this term as well, right? Yeah. Agree? Is that okay? Make sense to you? Since so the logic is that once you throw away this thing, you will get this the same. But in order to throw away this thing, this term must be bigger than this one. It means that this term also bigger than this one. Then we get that condition. Okay. So from here, so you will get right, you will get this one. We should give you a condition. This one. This is actually p. This is p square, right? Right. Okay. Up to here, then you could solve you could solve now a thing. Next, we're going to look at this. Okay, so we have this kind of condition now, right? No, let me explain what. So this this condition. So can you speculate what is the meaning of this condition here? So this is a wave number, right? Which is actually related to the wavelength, but this is the amplitude, right? Something to do with the amplitude. Then what can you tell me what is what do we have here? I mean, for this condition, the kind of physical meaning behind that, and it gets. Okay, so this is what we have. So the phase factor, right? Because well, of course that this k going to be in the exponential part, right? Which is actually related to the phase of the wave function, and then this is somehow you can think this is a rate of change of the amplitude somehow, right? Yeah. Then this that's what we have. Okay. So it means that somehow this is implied. Short wavelength, right? Or of course high frequency, right here, or this condition somehow. Right, short wavelength, you get high frequency. Okay, so now we have this kind of situation or the condition for the wave function that once we put this WKB approximation condition into those equation. I mean, only the first one, we haven't looked at this one yet. Okay, let's now look at this second one. Okay. Now we consider the equation actually this one. Well, you can solve this since you know that since it could not be zero, right? Otherwise, you don't have any wave function to work with. Then you know that this must be constant, right? Of course, with respect to the x, right here. So it means that your A is C Okay, right, yeah. And so you know what is the S plum from this, right here. Your S plum is P, right? So you can be P, right? Actually, it's plus and minus P, right? But we're going to take only the plus one. Otherwise, you will not get a real amplitude here, right? So that is the thing. So, okay, we are good here. So we solve for the A, but of course then we still need to fix what is the C, that what we're going to consider next. Okay. Now, from this relation, of course, from this here, let me now we consider this relation, right? It's plum, and you can, of course, that you can turn right. Yeah, you can do this, right? And of course, that it means that this S now is going to be a function of x1, x2, right? And actually, it means that this is nothing but the action. Oh, interesting, right? Because you know that the action is a functional of the, it's a functional, right? Which is, it depends on the function of x, right? Yeah. Okay. Yeah. Right. After you finish the integration. Interesting. That is the reason why I put the first remark, right? The first remark that actually when we take the wave function as an exponential of the s, right? You may wonder why we do that, or that it turned out to be that actually this is a function, this is the action, right? And of course, if you doubt about what I'm saying, you can check the dimension, right? Right, the dimension of this, yeah, going to give you exactly the same with the dimension of the action. Okay. Then, so once you get this thing, then you can write your solution now. So the solution is C over P. So it could be C tilde because square root C is the C itself. Then actually I just put the C, okay? But you have to keep in mind that actually, let me put a note here for you. So actually, it doesn't matter, right? It's just constant then. So, and then you get exponential okay. Here, your solution. but it's not complete yet, right? You still this is to be determined right here. That of course from what? From the initial value condition, right? And of course that if we consider this square, all right, this should give you somehow the plot, right, density somehow. So it means that this C, is a plot density of finding the particle at x, right, which is inversely proportional to the velocity at that point okay. Because the what proportional to the velocity at that point. I mean, well, because the p equal to mv, right? That is the reason why. Okay, you may probably heard that actually classically the probability that finding your particle actually inverse to the velocity. Yeah, that this is a proof classically, right? Okay, up to here are we good? Yes, of course. Okay, and let's continue. So now suppose we have a phase space. Okay, so you have a phase space. Yeah, which is actually okay. This is your trajectory, your system on phase space, and this point you call x plus, and this point you call x minus, right here, which is actually you plot. Suppose this is your potential, right? It's going to give you something like this, okay? This is the shape of your potential. Because I try to make it slowly change. I mean, otherwise it's going to not match the condition that I put here, right? It means that if your particle have moved up to this point, it have to move back and forth. Then it means that on this space, you see that your particle will move back and forth on this axis, right? But on the phase space, you will get another kind of trajectory. You get this kind of loop, right? The shape of the loop actually, let's note that the shape of the loop is actually depend on the V, right? It depends on what kind of V that you have here, then you will get, like in the case of simple harmonics, right? You get a parabola, then you get the ellipse out of that, right?
This is x plus, right?
Oh, then it means that I have to put the energy level here. Sorry, and we have to indicate that actually. Okay. Sorry. Okay. Thank you. All right. So. Okay. So I need a white chalk actually. Can you go to the office room and ask for the white chalk for me, please?พี่บอย Here. อ๋อพี่เชอรี่ก็ได้ครับ I need a white chalk and Thank you. Bum by the. Okay. So from this, can you see a problem? There is a problem here. Can you see that? Well, from this, there is a problem. As your P actually depends on this thing, right? I think there is 2m here, if I believe. All right, and as your x, I mean, it's mean that your p, yep, right. Of course, that at these 2 points, p must be 0, right? Because it's a turning point, which it actually stand on the x-axis. It means that, so then you will get this condition, right? Once you get condition, then this will be a problem. You see? Right, because well, what we did over here, that this is the probability that you could find your particle, which is actually proportional to 1 over square root p. But once you consider your system on this phase space, then you see that at the 2-point thing will be clash. Thing will clash, and then but well, there is a way out. Don't worry. Right? We could solve this thing, of course. Well, do not panic, okay? There is a way out of this, okay? So we move along the trajectory, right? The trajectory on the phase space. And approaching to the turning point. Suppose x minus here. We then switch to work with a wave function in the momentum representation. So it means that you need to do the Fourier transform. Okay. So suppose that your trajectory, sorry, it's not that good. Let me draw it again. So suppose you have this as your, okay, this is your x minus. So if you move here along this line, and then once you start to get very close to this point, so you need to do switching. Okay, to the momentum space, right? Just very close to the turning point, right? And then And then after passing this point x minus, we switch back to work with standard wave function again, which is actually again you need to do another Fourier transformation, right? Right. So let's draw it again. Suppose that's okay. You pass through this point. Okay. At this point, you're switching again from, okay. Oh, I forget to put tutor here. Okay. That is the trick to avoid that problem, right? And then, of course, that you, well, of course, then so we will do the same for the x plus, right? It means that in the case of x plus, you will get this kind of trajectory here, right? This is x plus. So you move along this line and get very close to it. Now it means at this point you do switching from x to p, right? And then after you get through, so here you do switching again from p to the x, right back, and then you just use this solution for the whole part until you get to that point again, right? That kind of thing. So this going to repeat itself, right? Because your particle will be moved back and forth, right? Then you have to apply this technique to, right? Okay. Hope you get the point. All right. Okay. Next. What time is it? Oh, interesting. Okay, so now we're going to consider a stationary phase condition, right? Suppose we consider this function that I call I. Okay. This is my fancy S. Fancy S. Okay. Of course, you know that for large fancy S, right? The phase is going to represent the phase of the function, right? The phase will oscillate very quick, right? All right, oscillate rapidly or very quick, all right? And on average, you get 0, right? Because it's oscillate very quick. Then on the average, then it means that you get nothing. Yeah, yeah, everywhere. Except as the extremum point, which is confined by using this condition. The point that gives this function critical, right? On all the other points, then you get you will get that actually the phase will take no contribution to this function. So to approximate compute the integral so we need a stationary methods by expanding this phase factor. Suppose that I would say that this XC represents a critical point. You know that what I mean by the critical point actually this extremal point can be called another name is critical point. It's the same. Okay? All right. So if you do this, you phi to the second order, right? Because the first order you get 0, right? You need to consider up to the second order, right? So you get this okay, approximately, then you know that this gives you 0. we also need to consider this amplitude as well around that critical point, right? We consider around this xc. So it means that this can be can do approximation as well to see whether this amplitude, the behavior of this amplitude around that the critical point. So you know that you get AXC, and of course the first order, right? Then we just keep up to the first order, okay? Okay? Then it means that, so once you put this thing into this integration and then you just ignore this term because it's very tiny, it means that this is going to be like constant and you can take it out. And this one also constant, right? You can take it out, right? Then so we have now this and this one. Square by employing the fact that right here. Okay, are we good here? Up to this. So now you can do it. You can do the integration now because it's very familiar with you now. Yeah. So what we're going to use, we call Flesch-Snell integral. It's somehow kind of the extend version of the Gaussian one. Okay. You can look at Google by yourself, of course. So you get IA, which is over 4. Okay, you will get this kind of thing, and then we get okay this. Oh. Are you okay? So, well, we get here. All right. Can I take like a 5-minute break? A 2-minute breaks maybe. I just need to go to the toilet. Okay. You might need to have a look, and then you may wonder what we do, why we doing this, right? What is it to do with the approximation, right? Ah.เพราะน่าจะเลิกช้าอันนี้ยังไปไม่ถึงไหนเลยเนี่ยโอเคเสียงเข้าเปล่าไม่เข้าโอเค let's continue okay so now so we're back to this equation, the full year. Okay, this one. And then you do the approximation. What you get is okay. So then, so the whole thing that we did earlier, that actually to apply to this integration, right? Which is you know about what is the XC, right? We could solve for that. right? This, put solve, then you put solve. See, okay. And so what you're going to have is that right here. Very simple. Okay. And you know what is the H-plan? Right. Which it actually is the P at critical point. Right. You get this condition. So you get this condition. Next, the sign of okay. So basically now you get what you want. So okay, so well, this symbol is telling you that this is going to be plus, if this is plus, if this minus, this is minus, okay? So and then this whole term representing the phase loss. Okay. And since this PC is finite and also is finite, then there is no problem plusing the turning point x minus. Okay? You see? Yeah. So it means that this two term is going to be some value, right? That is the thing. then there is no problem that if you use this kind of wave function at the point before you crossing the turning point, because you need to switch to this one, right? And then when you pass through the turning point, this is still valid. I mean that is valid. So what I did for the whole thing to give you a proof that actually it works, right? Yeah, that is a thing at the turning point by switching. So let me summary. So works at okay, that is a summary. All right, it works. It works. Why not? Beautifully. So now I'm going to define this new S, which is actually, if you look at this is nothing but the Lerchong transformation, right? All right. So if you think that this is going to behave like the one that go with the Lagrangian, right? And then this is the one that actually this action to go with the Hamiltonian one, right? Because it's a function of p, right? Yeah. Okay. And xc as a function of p. This is very tricky. Let's look at this carefully. We know that if you do this derivative, you get 1, right? And then you get, I do this, I still, of course, it still hold, right? And I swap it to be this one, right? Let me put C here. Okay. Maybe not. We just keep in mind that actually x as a function of p. Then otherwise, then going to make us confused. And this p as a function of x. Okay. So this going to give you so this is still 1. Then you get x prime, p prime, xc. You get this condition. Okay, and this is very cheating, a bit cheating, but why not? There's nothing wrong here. Can do. we can do math. We can do the math. We can follow the math, and we consider EP squared. So you will get 2p, right, this one. And at point x minus, right, which is something actually related to this thing. So you will get p squared x minus x to p x, right, which is actually to m. Okay. Can you see that actually we get this? Because your p is square root, right? When you did it, when you do derivative, and you will this square root will be go down and then cube each other, and then you left with okay. Okay. Of course, then for this, you get actually double palm of the s, which is actually less than 0, right? Okay. Then, hence, the phase loss term will be minus pi over 4. Okay, you will get a minus sign, as I mentioned here. Oh, there is a I there also. The I also here. Okay. 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 So now have a look again at this trajectory. So you start from here and then approaching to this, okay, and then get out. Like this, and then you start and end with this, and then around this, I mean, this, I should. Fish it. Okay, this is going to be your wave function before you passing through this point, and then after you passing through this point, you just do again the Fourier back to the standard one, right? Okay. At this point, we need to do the Fourier transform to get right here. Okay. So I said that this is in, and then this is out. Okay. So out. Okay. So oh, sorry. Okay, you need to use this Fourier, right? But I'm going to do the whole computation on that board. So what you get, you just plug the whole function, right? But px and this it's a bit I mean cumbersome, I mean huge thing to do, but it's not that difficult, I believe. Okay. But what we need to put is that we need to consider the PC. Okay. And that makes this function critical. So it means that you can, what you can do is that this, you can again do the variation. Okay, you do the variation, and what you get is it's going to be PC plus delta P, right? Oh, sorry, it should be critical. Yeah, sorry about that. And this okay. We again consider the expansion up to the second order, right? Then I put the oh shit, I put the approximation sign here. Okay. Dear. Okay. I need to close the bracket here as well. And then you can pull out all the constant, right? You can pull out all the constant, and you get this first order is 0 by claiming from what equation actually? Actually, we have here. Let me note here this term actually can be considered as right here, which is actually 0. We have this condition, right? Okay. Then you get that. Okay, we good. Okay, so again, you apply the integration again. What you get is okay. Now, using the relation that we have, put in here, then, okay, we're almost there. Okay, so now the phase factor will be pi over 2, right? Okay, and then this is over 1 over 2, right? Yeah. And you turn this function back, I mean s tilde, back to the standard s, right? You will get this one. So then it means that out can be take pi over 2 And so, well, for the wave function that's coming in, well, you see that there is phase difference, right? Okay. Friends, after you cross the turning point, right? That is the thing. By pi over 2, right? Yeah. Have been add up into your outgoing wave function, right? And this kind of whole business whole for both x plus and x minus right here. So for a complete loop, right? Complete trajectory, maybe. I mean, you have to you complete this one loop of the trajectory. Your wave function, up to this point will be this has been added up right here by I pi, right? Okay. Next, we need to solve for C, right? By so employing this thing square, right? Here. Let's put I here, initial. This is an initial condition, initial point. Okay. Xi here. We also, I moved to that, to the other slide. I think my handwriting somehow too big. I spent a lot of space to expanding, and I'm so damn tired to walking back and forth. And anyway, so you'll see, we know that we know this relation before, right here. That we have that this we have this relation before, right? And then we just put this in and in here, which is going to be the in and the wave function in, right? Is that okay to have this? Then, so for any wave function, you could find that this the ratio of this after you complete a loop, yeah, right. So after you complete the loop, right, if you do the ratio between any arbitrary wave function, right, and then get back to the same point, then this is represent a loop. The phase vector will be added up by pi, right? So after you complete a loop at this point P, right, it must be the same because you get back to the same point. The momentum must be the same, right, at that. Okay, so it means that this function, I mean, the wave function would be a single value function. It means that if you, after you complete a loop, when you get to the same, exactly the same initial point, you should get exactly the same wave function. Otherwise, then that is going to be a problem. Then you have to deal with in the complex analysis. Then you have your Riemann sheet. You have to go up around that is not what we want here, right? Because this is somehow we need a single value function. I mean, so this condition, I mean, after you apply this condition, this will get you 1. And so then this condition will be fulfilled, will be satisfied, maybe, if and only if this, I mean, this whole thing equal to 0 right here. Right. Not 0, actually, it could be any 2 pi n, right? Because this is the exponential function, right? Is the periodicity condition that, yeah. Okay. Then you get actually two pi n plus 1/2. This is the condition for a complete loop, right? And this is known as dx. Sorry about this. Yes. For Sommerfeld, quantization. Okay, have you ever heard about this? Bohr-Sommerfeld quantization. It's kind of attempt to quantize system from the classical point of view, because what we did so far is somehow related to the phase space, this kind of thing, right? And then we try to upgrade thing to be quantum, and then you get somehow this is kind of, because your system is bounded, you get the like quantization thing, right? Because it's bound, you know that it's bound, right? Then
Yes.
if it's not bound, then you will not get this kind of loop thing. That Bohr-Sommerfeld quantization. All right. That would be all. Then, well, what time is it now? Oh, this is okay. So I think I stop here for today. And so I'm going to give you homework, and then you can work with the example in the homework. I'm going to give you a guideline to do step by step with the homework, because I didn't have time to give you any example here. Sorry about that, because I spend a lot of time to explain, because today is a lot of math steps that we have to deal with, and then but I hope you get the point of this WKB approximation. And then we see tomorrow we have a tutorial class, and then you can we're going to resume it as normal, and then we can talk about quantum and non-thermodynamics with P-band, and we see again on Friday. And I think we might need to catch up some other day a bit at some point to make sure that actually we can finish the whole yeah, before your final examination. That's all for today. Thank you.